Very good afternoon, all. Welcome to the class. After the discussions on the files, I'm sure now you are eager to learn new data structures and new implementations. And that's what today we are going to start with. So I hope the files handling and complexity analysis you have understood well. Complexity analysis related discussions, what we have done was primarily we have focused on time complexity measurement. And for time complexity analysis, primarily we targeted to target of runtime during execution time, how much steps or approximate analysis of the how much time in terms of input will be needed, and order of growth was what we targeted to identify. So on basis of order of growth, effectively we go for some big O of n or big O of n log n or big O of n square or such kind of approximate analysis. Just one thing more to always remember is that big O is called as an upper bound asymptotic analysis, and this is called to be an upper bound time complexity. There are also lower bound and exact bound time complexities also that you are going to study next semester in more detail, and there the definition and all these meanings and etc. you will be studying in your DA course. So if you want to just have a more clarity, you can read from the book also, and you can get the exact definition and meaning also. But yes, more or less the clarity is with you that when nesting will be used, it will be going towards n square, n log n, or n depending on how we are using. Whenever you are going half of half size, that goes towards log n. So if I have an n step within which half each time, so half each time that will become whether then it's a nested half looping and inside. So that will mean n into log n, and that way it will become n log n, like in case of a best case of quick sort, etc. Or in case of a merge sort, it is n log n because every time half of half and n times repetition, etc. So you will study all that in detail. I'm not going more detailed at present, but now we go for going some new data structures, and we will see some more applications and usage. Till now, what we have studied was your arrays. Then we started with the stack. Then we started with the queue. And then we went with linked list. But all these having no hierarchical information. And we effectively have not discussed them to be under any category. They are primarily either sequential or direct access, but they grow in one direction. Mainly these become a kind of a linear storage or linear data structures. They grow linearly in this direction or this direction, left to right, array, etc., linked list or linked stack growing in reverse. But there are some non-linear data structures also. For example, when we say we have a tree, we have a graph, they just don't grow linearly in one direction. They grow in multi-dimensions, and then we call them as a non-linear data structures. Along with that, within that, a hierarchical tree is also a hierarchical data structure. Graph is not hierarchical, but tree and graph both are non-linear, and out of them, tree is a hierarchical also. Why we say it will be more clear when we look at certain examples. For example, all of you have a laptop or your desktop. Then on that, you have your file storage. How do you store your files? Into different folders or different files. Now, in a folder, you can have multiple files or subfolders. But in a file, can you have further another file or a folder? So no, it's a kind of terminating and terminal node, or effectively say that no further subdivision of no further nesting no further file or folder inside it. But folder will have again the same process. Many subfolders or files can be there inside. And same process applicable on subfolder further. All this effectively becomes a new kind of a storage system. And effectively, when I say my file system, my all file systems effectively are maintained by your operating system. They are stored in a particular hierarchical manner. What is that hierarchy? For example, you have various drives. You have C drive, you have D drive, and maybe you might have F drive, E drive. Pen drive also you attach, could be another folder or drive. So when I say a drive, for example, I have a C drive. By default, I say C drive has starting point as a root. C:/ means root. Within this, I can have multiple folders or files within this. For example, it can have one dev CPP folder. It might have one Windows folder. It might have, let's say, users folder. It might have a program files folder. And it might also have some file named as, let's say, file1.c. Or any other file with a similar name also can exist. Can be more files also. If it is a folder, it will have a further subdivision possible. But if it is a file, no further subdivision. Within this, again, I can have certain subfolders. Or I might have some file to .cpp or anything. Within these subfolders, each of them might have again further subdivisions and like that. Similarly, true for every one of them. But if you observe carefully, every subfolder hierarchically is a part of only one more outer folder. So this is what we call in this case is a special storage system. And such a storage system is called as a tree structure. So tree is another data structure which we are going to study now. File system effectively is stored into any drive. So each drive is using as a tree structure. For file storage, tree structure means each tree has a root. Then within the root, I can have multiple branches. Branch 1, branch 2, branch 3, and so and so. And there could be some leaf 1, could be leaf 2, etc., etc. If it is a leaf, it doesn't have further, but a branch might have another sub-branch 1, sub-branch 2, and maybe file 3. And similarly applicable for everyone, but no branching further for the leaves. So a branch, each branch can have many sub-branches and many files or leaves, I will say. Let's say call it as a leaf 3. So effectively, like a normal green tree which we have in the nature, effectively the same process. The only thing is in real life, you have a tree which grows bottom to top. You have a root, then root can have further branches. Each branch may have further sub-branches. The branch can further grow. Certain branches might have only leaves. Certain branches may have further sub-branches and leaves at any point. Finally, of course, they will have leaves and this process continues. So in real life, your tree is growing from the earth and topwards or bottom to top. Here we have a top to bottom. Root is on the top and bottom wise you are growing top to bottom. There are many more differences between a tree, real life tree versus your tree. you can compare and find so many things like watering is needed and all that. You can think of so many other funny examples. But technically, if you say trees of the file system versus real life trees, they are more or less very close to each other, and that's why they are called as a tree data structure. What does that mean now? Once I say that I have a tree data structure, primarily it has a parent-child relation also. It's a hierarchical structure, and hierarchical means there is a parent-child relationship. Why I call it as a parent-child relation? In our family also, if I make a family tree, so maybe let's say I have a root. Root could mean maybe my grandparent or grand-grandparents. Then from the root, whoever was that grandparent or well, they have further children. So child 1, child 2, and so and so. So like if I have grandparent, my grandparent has, let's say, 4 different children. So male or female, whatever, and all those were there. Then each of them have their own family further. Some might have a family, some might not have a family. So like this might be having no further family. So the family tree stops here. Others might have, say, somebody has 3 children, another child has 2 children, and like that. So you say, for these children, the parent is above. For these children, the parent is above. So this is their grandparent. No doubt about that. Similarly, from here, these are grandchildren. So all these terminology as it is used from the family tree, etc. And we say parent-child relation exists among every one of them, and that's why it is called as a hierarchical organization of the data. Not only that, maybe if I have a company, let's say it has a CEO, so one CEO might have certain directors, say 3 directors report to him, D1, D2, D3. Then under each director, maybe certain general managers are there. So GMs are there, GM1, GM2, and GM3, and so and so. Each of them further have, each of them have. Under GM1 GM, there could be many DGMs. Under DGMs, there could be many managers. Under managers, there could be many employees, like that. So again, it's a hierarchy of the relationship, boss and subordinate. So via tree, all this information is also stored, which we have not done till now. And this relationship is also used while doing certain programming and certain data storage. So this is what we call as a hierarchy. Secondly, it grows in many different dimensions like this. So it becomes non-linear storage. It doesn't go only vertical or horizontal in one direction or left, right, left direction. It is growing into any direction. Somebody might have, somebody might not have, somebody might have many of them. All this becomes a non-linear storage. Now, once we know this, I say, now based on this, we will formally define what is a tree, how to store, and how to use it in various situations. So my parent-child relation will be always maintained, and I have my file system also having root to be the parent, having first level children or first level division of its, they will be its children, then further subchildren, and like that. Then I say, let's formally define mathematically also tree. So I say a tree is effectively a set of nodes. Now, set of one or more nodes. So normally we say each tree has one or more nodes. Obviously, first node, which of them is obviously so such that a special node exists called root exists. So if I say tree, it's not empty tree. I say it's a special node called root. Then remaining nodes, effectively they are partitioned into disjoint sets. Disjoint sets has disjoint word will be very important, and I will explain what does it mean. Disjoint n sets, n will be obviously greater than equal to 0. So n disjoint sets will be there, which are effectively, I call them as a T1, T2, T3, and Tn, where each set is effectively nothing but it's called a subtree. So it has a disjoint sets or disjoint subtrees, effectively you could say, which are T1, T2, T3, and so and so. Meaning, let's say I had this as a root. Let's say I have data 50. Now it might have lots of nodes under this. Each of this is one set. This is T1 set. This is T2 set. This is a T3, T4, and so, whether it's a file or anything. So we have this kind of things. And total number of nodes are hierarchically arranged in a way that none of the element of T1 is common with the T2 or T2 with the T3. All these are part of, let's say, child 0 of 50. All T2 nodes are effectively under only one hierarchy, which is under hierarchy child 1. So each node has always one parent. It will never have double linking. That is obvious, but programming wise, if we don't force this, it will be not guaranteed. Real life, parents are only one set, one mother, one father, biologically only that. But yes, it means, let's say if 30 is this child, 30 has another 60 as another child. Now it will be not possible that, let's say this is 40. So if this exists, this link is impossible. That is what is guaranteed. If this is a part of T1, none of them will be part of a T2. So nobody will be part of another set also. So this linking, cross-linking, etc., or that will never happen. That is what is the meaning of disjoint. Knowing this, effectively now, I can see my file system also means C:/ being your root. Each folder, say this folder 1 is your T1, that is folder 1. Folder 2, and so, each of them. This itself is a further subtree. Further subtree means it becomes a recursive definition. If I just say subtree means another tree, so that means within the definition of the tree, the same word tree is reused. Just to say subtree, so that we just knew hierarchy. Otherwise, it is recursive definition. The definition of tree again used a tree word, meaning this T1 itself is another tree. T1 tree means if this tree exists, if n is greater than 0, so T1 exists, then it will have a root, and root will have further sub-branches. This tree exists, it will mean this root will exist and further sub-branches and like that. So effectively now I can say my tree structure becomes very simple and very useful, and I have lot of subtrees present which are recursive. Then we say, for example, if I have a data 30, say I have 50, 70, 35, 40, in whatever way, they might have further subchildren, subtrees. So effectively, this is again another tree with 50 as root. And similarly, I can have this another subtree, this another subtree. This could have only last element, let's say 55, no further division. So this could be just with a root node and no further partition. So this is again a tree with root 55 and no children and no subtrees. So, but overall, this is again a root with many subtrees, one subtree with 50, one subtree with 70, 35, 40, 55, like this. Having said that, then we define level of the tree. So root we always say to exist at level 1. Children of level 1, that is children of root, are always said to be at level 2. Similarly, the next level nodes of any one, they will be said to be level 3, and level grows like this. So root is always at level 1, and accordingly, your children will be accordingly higher levels. So a level is defined like this. Then we define height of a tree. Height of a tree is always the highest level of any node of the tree. Now, that means that my tree 40 might grow like this. So level 2, level 3, level 4, level 5, level 6. Say this value is 77. 77 is at level 6. So my height will be 6. Even if other nodes might be terminating before, if it is the highest level, then this will be called as the height. Similarly, we define a degree of a node. Degree of a node means nothing but number of children it has. So somebody might have degree 0, somebody might have degree 1, somebody might have degree 10, somebody might have degree 7, like this. And degree of the tree will be the highest degree, obviously, out of all nodes of any node of the tree. Same way the height was defined. So these words will be used in various discussions, but all these words are logically very simple to understand, and we can have them. So I can always say we have these children, or we have the ancestors, or grandchildren, parent, degree, height, ancestor. Ancestor means, of course, the purvaj, like my parent was my one ancestor, next level ancestor was grandparent, grandparent was higher level of ancestors. So ancestors, etc., always happen. So then similarly, children of the same level, they are called as siblings. So of same parent, they are sisters or brothers and sisters. So they are called as a sibling. All these words are same as from the family tree take. So knowing this, now we have to think of implementation. How we will implement this? So obviously I will say, I need a data structure. What data structure? For example, I need for any root, I'm talking of a root node, I need a data. Data could be as simple as integers, but it could be many more than that. Now it can have many children. So maybe I'll say, this is your child 0, this is your child 1, and so and so. How many? So there can be theoretically infinite children, but for implementation angle, we will assume certain number of maximum children. Maximum degree I will assume. Let's say I say 50. So then I will say, I can treat them to have various child 0 to child 49 as various children so that I can refer them. If I have to implement that, obviously I will have a type def, struct node, and I can do all that. In this, first of all, your data. So if I have a simplest data, I can have an integer. but all data members, whatever I mean, whatever fields I need, could be there. Then I need children. Children what? Each children is another tree. Another tree means pointer to the tree only, because if I want to store the full tree, I need a pointer. Pointer means I need a struct node star. And I need a lot of children. Like in case of a doubly linked list, I have previous and forward, back and next. In singly linked list 1, in a stack I had back. Here I have a lot of children, child 0, child 1, child 2. Either I declare like this, or all this can be simply declared as an array of pointers. So I can have child to be an array of what data type? Of pointer to node. So ideally in this case, I will require array of pointers to be used and implemented. And all children will be treated in the identical manner. They will be named as child I, child 0 to child 49. And maximum limit is fixed. So this could be the way to declare and use. Of course, the detailed programming on this you are going to do later. Whenever you do this in advanced data structures, you will study a tree and various other kind of special trees like a B tree algorithm in DA you will study. Then along with this red-black trees, splay trees, and there are many other. This semester we have a simple version to be done, which we call as a binary tree. Effectively, as it says, number of children will be binary. We will not have 50 children or those many children allowed, because that means a lot of programming complexity, array of pointers to be used. Binary tree means maximum 2 children. Of course, it has a different kind of applications also. So my file system will be stored as a tree. It cannot be stored as a binary tree because you have children limit. But binary tree has its own lot of applications. So binary tree will mean effectively if I have a node, it can have a maximum 2 children. Of course, the relation of hierarchy will be still there. Let's say 30, 50, 60. 50 might have maximum 2 children, let's say 45, but need not be both. Somebody could have 1 children, somebody could not have any children. Let's say this is 33, this is 45, this is 66, and like this. So we say there are 2 children, one we call as a left child, other we call as a right child. In a tree, each child was equally considered, but here left and right, 2 different names are used. And if need be, they can have different properties also. So there will be some special usage where left and right child will have a different properties. In family, normally we say for parents, all children are equal or they are treated in the same way. But in a binary tree, left child could be treated in a different way, right child could be treated in a different way. So, for example, we have a special tree which is called as a BST, where this property will be valid. So, in a real life, they are not differentiated, theoretically at least. But yes, in programming, we have the freedom. If we need, we can differentiate. Even if we don't differentiate, they will be guaranteedly referred with 2 different identical names. One will be called as a left, other will be called right. And symbolically showing this, it means 50 has only left child towards 45, but 60 has only right child, which is 33. 33 has both children again. And of course, this we call as a root. But indirectly, if you see here also, this itself is another binary tree. This itself is another binary tree. So whatever definition of a tree was made, almost a similar definition is still applicable. And I can say my binary tree is also mathematically defined in the similar manner. So now let's try to mathematically define binary tree in the similar manner what we have already done for the trees. So I say again, in the similar way, it will be a recursive definition. And I say it's a effectively finite set of nodes. Of course, finite set of nodes, but it could be either empty also. In a tree, we didn't say that it could be empty, but here we say we have empty, and this empty word use is useful for writing it in a simpler manner. Either empty or it has first thing a special node called as your root, and secondly, two children which are effectively two subtrees. So sub-binary trees you could say, because same recursive definition will be applicable. Sub-binary trees named as left and right. Now, indirectly, this means this can be empty also, because you can easily see that this is a recursive definition. With the definition, we are using the same word. Recursive definition says that although I am saying two subtrees, two sub-binary trees, but each of them or one of them or both of them can be empty also. So it's not compulsory that both children will always exist. It means maximum two children, but for certain nodes, it could be zero child, it could be one child, or it could be two children. Depending on, some of them could be empty, some of them could not be empty. Effectively meaning that if I have any data, I will have some relationship hierarchically in this form. Let's say 35, say 45. This might have 70. This might have, let's say, 40. This might have only right child, could be, let's say, 33. This might have only left child, let's say, 42. This could have only right child, 36. This could have both children, like this. So this is your level 1, level 2, level 3, level 4, level 5, level 6. Say 72 and let's say 37. So height of the tree becomes 6. Degree is guaranteedly 2 because my binary tree is there, so degree is already there. Now, effectively, if I have to declare your structure, so my binary tree node structure becomes a simple. So if I say, let's say struct binary tree type def, if you need, you can do. Of course, data. So if I want only integer data, int, but otherwise it could be any data. So you have a data, plus you have two pointers. One we call as a left pointer, other we call as a right pointer. So now I can have struct binary tree pointer the way we had in linked list. Star left, star right. That's it. And this becomes your binary tree node. But with this compare, in case of a linked list, doubly linked list, what you did was, there also you had a data. There also you had a previous pointer or a back pointer. And here you had next pointer. Now we have a data and we have a left pointer. We have a right pointer. So in case of a binary tree, things look very identical to what we have discussed in binary in DLL doubly linked list, but this was a linear storage. No hierarchy was being discussed. Here, hierarchy is important. This side, we can have another full subtree. which is all child of this root, and this side can be another subtree. So here hierarchy exists. Further, all of these are disjoint sets, all recursively applicable, which was not true in case of a DLL. So recursively, lot of things will work directly, and all these things will work in this particular manner. And automatically giving a hint that a lot of recursion will be needed for its programming, which was not needed for DLL programming. For example, now I say first work will be always, let's say, create a binary tree. So the question is how to create it. Create, I mean that my aim is read and store inside your program the tree which I have drawn on paper. Like I have just drawn one side, I want this tree to be used for further processing. For example, this tree. I want this tree to be read and create this one. So I mean create means I want to have some logic so that I can read any structure like this. User has drawn it on paper. User should be able to conveniently input this. So how to input? Of course, root you can start. So remember, for a tree, for binary tree, like in case of a linked list, only root is stored. So we will always store only root pointer, rest all is linked via root. It's a kind of a start pointer for the linked list or for the binary tree. So what to do? Ultimately, I mean, this root will be stored perfectly fine. I can create this node, but then sometimes I have left child as well as right child both. Then for 35, I have both, but for 45, only one. For 70, nothing. So I could say this will be null. Right child will also be null. That will be the stopping point. But 35 needs this children to be read. For example, this might have like this. This might have like this. Let's say this is 27. This is 23. This might have further like this. So how will you read? Maybe you will say, okay, read 30 is left child. You read 35. 35 is left child, 70. 70 is left child, maybe null. 70 is right child. But once 70 is over, should I go to 35? Maybe I know some way, previous pointer I will maintain. Then 35 to you come to 40, 40 to 27, 27 to 23. 23 says this side null, fine. You read 25, 20 side said both null, fine. Now after 25, should I resume at 27 or not? Or it has been completed, maybe I'll say I have to know that. Then 45 is also pending, 30 is also pending. After 27, should I resume at 40 or not? No idea. Where to go after which node? And how to maintain all this information. Effectively, I mean to say is, if you think of making certain loop, while, etc., it's going to be a difficult way of reading. Think of making the logic to read such logic iteratively. So logic is going to be difficult because I have to resume at different positions. Maybe you have to store your information into stack, etc., for knowing which node has been completed for both children, which has been completed only for left child, which has been checked for right or not, then whether it is pending or not. But then if you use all this, it is indirectly equivalent to having the recursive usage. So recursive implementation will be much easier and much more simple to understand also. And easy to code also. Because by definition, tree has a lot of recursion. So we will understand that this thing, try iterative, you will find it very difficult and still you might be not able to make a good logic for this. If you can make, that's really good. But what we are going to see today is we are going to make it as a recursive logic, and which will be much more simpler and easier to understand. So I say, let's try to make recursive logic. So I say creation to be read I mean I will have a create binary tree as a function, and of course it will return the root. Return has to be, or some way I have to do. So maybe I will say node star will be there and create, etc. This function, if I need any parameters, I have to do something. So I'll say create your binary tree, but of course node star to be returned, because start, root, etc. needs to be returned. So now think of what can be the recursive logic. I say my logic is nothing difficult. For example, I said this is 30, this is my root, and then on the left side also I have a subtree. And I say on the right side also, currently I have a right subtree. So can I write a logic which tries to read also in the similar identical recursive manner? This picture clearly tells how I can implement. Of course, what I need to start. So let's, for the time being, assume that root node always exists. Simple coding. So special situation we will handle later. Root node always exists and other nodes might or might not exist. If I assume root, that means currently first time root is guaranteed there. What is my first step? I have to do malloc. So I will say root equal to malloc with whatever logic I have to do. That will be obviously first step. Second step. First step means I have read 30. I have created this node and this pointer is root. Now what next? What is the data inside? This data needs to be read. Whatever data user tells, I will store this data. Done. First, second step. Third step. Recursively, I will say read left subtree. Create or read this side. So I'll say effectively this means create left subtree. Now, create a tree is being used and the same function being used to call it for the left side is becoming recursive call. But I assume somehow this will work. Similarly, I will say create right subtree. That's again a recursive call. And this way I say, if I assume recursion works well, which is the basic assumption, I'll say this side will be read like 35, 70, 40, and so and so. Similarly, this side I have read 45, 33, then I had 42, and I'm able to read whatever logic I have thought of. Let's assume this all gets read correctly, means all this gets properly created, and this is the corresponding root pointer created. This all works well. And this is the logic which I'm using. But I'm trying to make this call as recursive always will mean infinite recursion. Recursion is not stopping. We have the thumb rule, recursion cannot be infinite. Secondly, for example, 33 does not have a right child, then why we are unnecessarily making a call? 70 does not have any children, why we are making a call? All these have to be simply null. So recursion cannot be permanent and infinite looping will happen otherwise also. So what I say is, now I have to see whether I need to do or not. So maybe if I say data is -1, stop that, could be one way. But that will mean I should be able to read or create this node, store here -1 and then ignore, not a good way. Or take an extra variable, read that as -1. If -1, then don't create. But how to do that? I said, I have done reading this. This is a recursive call. Next recursion will only come to know whether it was -1 or not. Recursion will tell, but if I go that way, how this linking will be established. So becomes a challenge. So maybe I can say simple way could be that ask the user if it has left child or not. If it has left child, then you will give a recursive call, otherwise not. So third step, I'll say if root has left child, so I will confirm from the user by asking choice 1 or 0. 1 means exist and 0 means child doesn't exist. Or 1 or 0 -1, whatever you say, you can take that. If root has left child, I will have this call, else what to do. So whenever I'm writing F, the corresponding else means, for example, if a 30 has no left child, then I should say this should become null and this should be a recursive reading. So I will say else will mean effectively left child to be equal to null. And similarly for the right child also. So effectively, now I write it in more clear words. So it's a create function. If parameter needed, my first step is malloc to the root. If I say root being malloc, what is happening? Let me just keep a picture and no page here and show you parallelly what is happening. So by this process, what I have done, node created, which is named as root, done. First step. Then second step, data to be read, say 30 or whatever data. So 30 read. Third, if left child exists, means I will say choice taken. Effectively, I have to make a recursive call for create any parameter or not, I have to think of, but that will mean the same recursive call. Recursive call, you can assume works well, means that if let's assume this was existing, so in that iteration, 35 will be read as a root, its link will be maintained as a 70, this link will be maintained as a 40, this has right child, that will be done, everything done and read properly. And this left root of left tree will be returned. So by recursive call, this activity is complete. But I have not maintained this link. So this linking has to be done. This you have to ensure. Similarly, fourth step, or else I will say the left child is null. Fourth step, similarly for the right child, exists. You will have the create function recursively called, else obviously null. And what else? As I have said, it's a node star. The created tree is to be returned. created tree is effectively having your root as its starting node. So this node is to be returned. This will become overall logic, but we have to ensure proper linking because that step we have not explicitly written anywhere. And what linking is needed is 30 was red. This left subtree is red. This pointer is available to me. I should be able to do this linking. If this exists, otherwise this should be null. Similarly, through recursive call, this reading done, all tree will be assumed if ready. Recursively, it will be automatically done. This node pointer is being returned. I should be able to link through this. So once you have done this, wherever null was, otherwise it will be null somewhere, and then this will become overall root. And then this is being returned, your creation is complete. So I will stop here and ask you to try to complete this code. And ensure that it is able to work well. If next class we will discuss and finally write the code and see the intricacies under this process. I'm leaving here, not writing the syntax intentionally so that you try and think of the possibilities or think and then find what you are not able to implement. Where are you stuck? Why you are not able to write the logic or think? Because recursion understanding is slightly difficult. So once you get this clarity that where you are not able to think, next class will tell you how you should have thought, how should you have applied your mind, and then that doubt would not have come. Bye-bye. All the best to all of you. Next class, we are going to have all this complete.